MCEN 1131 Engineering Mechanics Statics Equilibrium Part 1 Prepared by Mirko Dumanovic. Equilibrium and free body diagrams. Upon completion of this chapter, you will be able to 1. Draw complete free body diagrams of the whole or part of any given mechanism, and 2. Apply the three equations of equilibrium to any given free body diagram. Equilibrium is the state of a system in which the variables used to describe the system do not change. Equilibrium can be stable, unstable, or neutral. In a stable equilibrium, if a small push away from equilibrium is applied, the system will return itself to the equilibrium state. A good example of this is a pendulum hanging straight down. In an unstable equilibrium, if a small push away from equilibrium is applied, the system will move further away from its equilibrium state. Neutral equilibrium is the kind of equilibrium of a body so placed that when moved slightly, it neither tends to return to its former position nor depart significantly from it. Think of a perfect sphere or a cylinder on a horizontal plane. It is helpful to think about equilibrium states in the context of real-world examples. Consider the figures here. A free body diagram is a diagram that shows an object or body with all supports removed and replaced by the forces acting upon it. Objects depicted in a free body diagram appear to be floating freely in space. Drawing a free body diagram is a necessary first step in calculating the forces acting upon an object. Free body diagrams depict objects in a state of static equilibrium. Static means that the object in question is not moving, and equilibrium means that the forces acting upon the object are all equal and opposite or balanced to one another. Consider figures 1 and 2 at the bottom of the page and follow along. Figure 2 depicts the free body diagram of the crate shown in figure 1. The tension in the rope applied to the pulley is shown as a force of 60 pounds pulling upward on the crate. The gravity acting upon the crate is shown as a force of 100 pounds acting downward on the crate. The floor is supporting the crate. The support of the floor is shown as an upward force N. A free body diagram of an object must show all of the forces acting on the object. It is recommended that you do a final check to ensure that no forces have been omitted and that your free body diagram is complete. There are three forces on free body diagrams. 1. Applied forces. 2. Non-applied forces such as weight. And 3. Forces replacing a support or section. Forces can be called acting or reacting. Acting forces include applied forces and weight. Due to these acting forces, the forces at a support would react accordingly and are therefore known as reactions. The importance of a complete and correct free body diagram cannot be overemphasized. Checking it is time well spent. Consider the following. Who uses them? Well, every organized problem solver. What are they? A picture upon which calculations are based. When are they used? Well, always. Where are they used? As step 1 of all problems involving forces. Why are they used? To show clear documentation of a problem solution. How accurate must they be? 100%, except for assumed directions. The three equations of equilibrium. To begin, we will consider only coplanar force systems. Recall that coplanar forces are forces that act in only one plane. All of the forces that we have analyzed so far have been coplanar. The chair in which you sit is in static equilibrium. It is not moving up or down. Therefore, the total upward vertical forces acting on the chair are equal to the total downward vertical forces acting upon it. In other words, your weight and the chair's weight are equal to the force of the floor pushing up on the chair. For total static equilibrium, three requirements must be met. 1. The vertical forces must balance. 2. The horizontal forces must balance. And 3. The moments about any given point must also balance. In other words, the sum of vertical forces must equal 0, the sum of horizontal forces must equal to 0, and the sum of moments about a given point must equal 0. Free body diagram drawing conventions. When drawing free body diagrams and replacing supports with equivalent supporting forces, you must employ some definitive assumptions and conventions. The table below shows the forces drawn to replace various supports or connections to members. Follow along. Roller. The roller cannot exert a horizontal force, therefore only a force perpendicular to the surface is present. Smooth surface. Zero friction is assumed, therefore only one force, that perpendicular to the surface, is present. Slot. The same principle applies as to that of the smooth surface. There is only one force present, that which is perpendicular to the slot. Pinned connection. Both horizontal and vertical components must be assumed at the pinned connection unless it is on a roller or a smooth surface. The orientation of support is immaterial. Horizontal and vertical forces must still be assumed. Cable. There's always a single force pulling in the direction of the cable. Homework. Read Chapter 4 up to page 98 and complete the practice examples and problems from the book as well as those provided by the instructor.